Okay, so we were talking about oxidation numbers, and we're looking at how do you determine the oxidation number of NO3, KNO3 here. Okay, so oxygen has a -2 oxidation number, not -6, even though there's -6 charges from the oxygens. That's not how we report it. We say oxygen has a -2 oxidation number. Okay, what is the oxidation number of potassium? +1. How do you know? Does it ever change? No, it's constant. What about the second column? Same thing. Okay, those guys always have +1. These guys always have +2. Hydrogen +1 most of the time. Okay, rare occasions it would be -1. Okay, but for mostly what we're doing is +1. Okay, oxygen -2, unless it's a peroxide, then it's -1. Okay, but you're not going to see a lot of peroxides. A peroxide is like hydrogen peroxide. Whoa. Okay, here this is +1 for hydrogen, right? So that means it's -1 for the oxygen to balance it, right? So that's one of the only situations you would see that. Otherwise, you can count on oxygen being -2, and you need to. Fluorine, -1. You can count on that. But basically everything else, you can't. I can't look at nitrogen on the periodic table and say it's going to be -3 because this is not ionic. That is not an ionic nitrogen. If it was an ion of nitrogen, yes, it would be -3. But it's not. This is a covalent compound, NO3. Okay? Whoops. It's a covalent compound. So that means I have to figure out what the oxidation number of this nitrogen is with these 3 oxygens surrounding it. Each one has a -2 charge. So what is the oxidation number of the nitrogen? +5. Right? Because it has to, in the compound here, it has to balance. I have -6 charges plus I have balanced one of them with this potassium, and that leaves me 5 positive charges left over. Okay? So that's how we're doing oxidation numbers. So make sure you're familiar with how to do those and that you can answer a question. Because sometimes it's a chemical reaction, okay, where something changes its oxidation number from one side of the reaction to the other side. And you need to be able to, if that nitrogen, let's say it went from NO3 minus, okay, on one side of the reaction to, so in other words, KNO3 over here to, let's say, potassium plus NO2 plus O2. Okay? Let's say I did this. So this nitrogen we know is +5, right? What is the nitrogen over here? Okay, this is -2, that's -4. Sorry, you know what, I should have kept that at a -1 charge. Excuse me. So let's just say it went to KNO2 plus O2. Okay, so, and we can get rid of this -1 charge. Okay, so that's -2, that's -4. This is +1. What's the nitrogen? +3. Okay? So there's that +3. It went from +5 to +3. So I have to be able to do this sometimes in a chemical reaction to identify what was oxidized and what was reduced. Because what did oxygen do? It went from -2 to what? 0. Okay? So if that's the case, what was oxidized? Oxygen lost electrons. So it was oxidized. So what was reduced? Nitrogen was reduced. Okay? The potassium, did it change oxidation state? No. Did the oxygen in the here and here change oxidation state? No. So they stayed the same, so they're not part of this oxidation reduction reaction. This was oxidized, this was reduced. So what is the oxidizing agent?
Nitrogen.
Nitrogen is the oxidizing agent. Oxygen is the reducing agent. Okay? So that's how, so this would be, yes?
So the agent is always on the left side of the...
Yes, that's right. Okay? So that's how I would do these oxidation reduction, identifying oxidation reduction based on the oxidation numbers that I calculate. Okay? All right. Then, a really big part of your test, stoichiometry. Okay? Know how to calculate amounts of products or reactants given a starting amount and a balanced chemical equation. So I've given a few examples there. Okay? Balanced chemical equation. You have 2H2 plus O2 gives you 2H2O. Okay? So, this is stoichiometry. Okay? If you start with grams, you have to convert to the moles of A, so you can convert to the moles of B, the other thing, so that you can get to the grams of B. GMMG. Okay? I start with the grams of A, I go to the moles of A, I then go to the moles of B so I can get to the grams of B. Okay? That's this actually, M of A to M of B, that's the stoichiometry part. This is just so I can answer the question. Or they gave me grams to start with. Well, I have to convert to moles from the grams so that I can convert to the other thing. Okay? So in the water equation here, the example was if you're given 3.7 grams of hydrogen, reacts with excess oxygen, okay, how many grams of water are produced? Okay, so we have a balanced chemical equation, 2H2 plus O2 gives me 2H2O. So if I have 3.7 grams of H2, I'm going to go to the grams of H2O. This one is in excess, meaning it's not part of the calculation. So I can start with my 3.7 grams of H2 and convert to the grams of water, G of A to the moles of A to the moles of the other thing, the new thing, which is water, to the grams of water. I drop my units. So if I write my process along the top, I'll see that it's correct. Okay? Grams of H2 to the moles of H2 to the moles of H2O to the grams of H2O. And then once I have this process figured out, I just have to drop my units. Grams, H2. Moles, H2. Moles, H2O. Okay? And then I can just fill in. I can just fill everything in. Here, grams and moles. Moles are always what number?
1.
Good. Okay? Do not put the coefficient there. That's the biggest mistake I see. Don't put the coefficient. I don't want to know how many grams there are for 2 moles of hydrogen. I want to know how many grams there are for every 1 mole of hydrogen. So there's 2 grams of H2 for every 1 mole of H2. That's what I want to know. Okay? The coefficients come in right here. Mole to mole relationships. If I'm going to convert from H2 to H2O, I need to know their stoichiometric relationships. Where do I find them? No?
Oh, I mean the balanced equation.
Balanced chemical equation. Good. So 2 to 2. Right? 2 moles of H2O for every 2 moles of H2. Those are the coefficients. And then, once again, grams and moles. Moles are always 1 Grams, where do I find the gram amount here? Periodic table. So I have oxygen, which is 16, hydrogen, which is 1, but there's 2 of them. So 16 plus 2, 18 grams of water for every 1 mole of it. Okay? So that's the process. G, M, M, G. That's the longest I could be given. What if I had, what if they had started with the grams, 3.7 grams of H2, and they wanted to know how many moles of O2 react with it? Okay, so how many moles of O2? Well, I would go grams of H2 to the moles of H2 to what? Moles of O2. That's what I'm trying, and I would stop because that answers the question. I wouldn't keep going to the grams of O2. That would be unnecessary. I stop here because that answers the question. How many moles of O2? I stop. Okay? So, grams of H2, moles of H2. So, grams of moles, moles are 1, grams are 2. Moles, what are the numbers I'm going to put here for this relationship? 1 over 2. Those are my coefficients. Okay? So 3.7 divided by 4. That's what I'm going to get here. Yes?
On the top there, should it be 2H2 then?
Yes. Thanks. That wasn't very balanced, was it? Okay. Yes, that's H2. I'm sorry. I was writing H2 all over the place here. I forgot to write it up there. Okay. Yeah, that doesn't work. Okay. Hydrogen does not exist as a single hydrogen. It exists as a diatomic molecule. Okay, so that's how we would work these types of questions. Okay, but sometimes they ask maybe a question like, if you have 3 grams of H2 and 25 grams of O2, how much water is produced? Or what is the theoretical amount of water? What is the theoretical yield of water? Starting with those amounts. How am I going to do that? What's that? That's for percent yield. We'll do a percent yield question after we do this theoretical. I have to figure out which one is limiting. Why? The excess I don't use. The limiting I do. So if I want to find out how much water is produced, it will be based on one of these. But which one? I have to figure that out. Because I need to either start with 3 grams of H2 and go to water, or I need to start with 25 grams of O2 and go to water. How am I going to figure out which one is limiting? Pick one. It doesn't matter which one, and go to the other thing and figure out how much would react with it. Okay? So if I have 3 grams of H2, how many grams of O2 would react with 3 grams of H2? That's what I want to know. That's going to tell me whether H2 is limiting or is in excess. Okay? So I have 3 grams of H2. I want to convert it to O2, which means I have to first convert it from grams to moles of H2. Now that it's in the moles of H2, I can convert to the what am I going to go to? Now that I'm in H2, I'm going to go to what? Moles of O2. Do I stop there? No, because I can't compare moles of O2 to the grams of H2. But I can compare the grams of O2 to the grams of H2. So, grams of O2. Okay? So, drop my units. Thanks. Okay? Fill it in. grams are moles. Moles are 1. Grams are 2. What is this relationship according to my balanced chemical equation? Okay, 1 over 2. Grams of O2, what do I put there? 32 over 1. 32 grams of O2 for every 1 mole of it. Okay? 3 times 32 divided by 4. What is that? Say it again. 24? 24 grams of O2. So, if I have 3 grams of H2, how much oxygen would react with it?
24 grams.
Do I have 24 grams? Yes, I have more than that, right? I have 25 grams. So what does that mean? Which one's limiting? Okay, so this one is limiting. This one is... it's going to drive me crazy. That one is excess, right? Okay, so have I answered the question? No, not yet. How am I going to answer the question? Am I going to start with my 3 grams of H2 or my 25 grams of O2?
3 grams.
Good. So I start with the 3 grams of H2 again. Okay? So I'm going to take my 3 grams of H2. And I'm going to now go to what? Grams of H2O, because that's what I want to find the theoretical yield. Theoretical yields are in gram amounts. So grams of H2 to the moles of H2 to the moles of H2O to the grams of H2O. Okay, drop my units. Grams of H2, moles of H2, moles of H2O. Okay? 1 to 2, 2 to 2, 18 to 1. So, 3 times 2 times 18 divided by 4, what do you guys find?
27.
Say it again?
27 grams.
27 grams of H2O. That makes sense. 24 plus 3, 27, right? 24 grams of oxygen and 3 grams of hydrogen gives me 27 grams of H2. How many grams of oxygen were not used? Just 1 gram, right? So 24 grams of the oxygen was used. There's 1 gram of oxygen left over. Okay? Because we can subtract, we should have made, we used 24 grams, so that means I can take 25 minus 24, and that's going to tell me how many grams of oxygen are left. Right? Okay? So this is a theoretical yield. Okay? So what if I go to the laboratory, I run this reaction, and I collect, let's say, 23.6 grams of water? How do I find my percent yield?
Actual over theoretical.
Okay, so which one's my actual yield?
23.6.
Okay, actual over theoretical times 100. So the theoretical one is always the calculated one. The actual, they would have to give you because you're not in the laboratory. You're not actually in there collecting it. So you would have to be given that in the question. So 23.6 grams of H2O over 27 grams of H2O times 100. Okay, what is my percent yield here? I'm sorry, say it again. 87.4%. Okay, that's how good I did. Okay, so that pretty much covers all that. Those are the ideas that you need to make sure that you sure up before our test coming up.
That's it.
Oh, you know what? Something that didn't make it on here. Oh, no, it's on here. From precipitation. From precipitation tables, be able to identify if a precipitate will form. Okay? So you'll be given that as a reference material, the precipitation chart. Okay? And
What chart are you going to give us? I mean, there's some easier to read, than others. One of the book is crap, is what I'm saying.
Yeah, it is a little.
That's
that one in that book?
In this book, yeah.
that's trash.
Which one do you like?
The one that showed. I don't know. I got it from the class. Because we're only going to have an hour and 15 minutes, right?
Mm-hmm. How's this one?
That one's cool.
Is that one that you guys?
Yeah.
Okay, I'll get that one on there then. Okay, we can use it. If this is one that you guys feel is you can understand well enough, we can.
So on those,
That's
like,
one.
Where the insoluble exceptions, the exceptions are only for the halides, right? So see the way the
These ones?
Yeah.
Yes.
Only see the one in the book. It has it, but you kind of get confused
Okay, we won't use that one.
of what's like actually.
Okay. If that one's confusing, we won't use it. So here, if it's in line with it, those are the exceptions for that thing.
So like basically.
So calcium is not an exception of halides, but calcium is an exception for sulfates.
And so like for like nitrates, there is no exception.
There are no exceptions for nitrates.
That's, yeah.
If you have a nitrate on something, it is always soluble. If you have a sodium on something, it is always soluble. Carbonates are insoluble unless they're with one of these guys, which are always soluble, right? So, so that's how we're reading this. Hydroxides, insoluble unless it's an alkali metal, or barium. So barium's one of those few exceptions that will cause it to be soluble if it's with a hydroxide and it's not an alkali metal. Okay. Okay. So that's precipitation. So be able to read these charts. And do you guys have access to these notes? You should, right? I think if you go to your pages, lecture notes, okay, you should pull up an online version of these notes.
When's the homework going to be due?
I'm going to set it to be due by the test. Chapter 4? Yeah. Okay, so let's see here. So if you click on that little 3 boxes, here you can go to your class, 1311, and then you can just go through the different pages of notes, and it'll pull them up. Okay, so there's a lot of stuff on here. Okay. So. Here's stoichiometry. So you can pull up all those notes. Okay. So you should have access to that. If it's not letting you on, let me know, and so I can fix it. Okay. Where are we? Back here. Okay, so we're going to continue now in chapter 6. So we left off talking about these orbitals, the different shapes of these orbitals in chapter 6. So now let's look at these energy diagrams for the electrons. So an energy diagram is showing you how electrons will feel based on the energy associated with them. Okay? So when I say 1s, what does that mean? Means first energy level. So we have a nucleus, and surrounding that nucleus is one orbital, and it could have one electron in it, which would be hydrogen, if it had one. If it had two, it would be helium. Okay? So we have one electron, two electron, that's helium. So the 1s, and why do I say it's the S? Because here on my periodic table, the S's are these first two columns. So hydrogen and helium would actually be over here for what we're talking about. Hydrogen and helium in the 1s. Okay? Sub-energy level S. What is this sub-energy level? P. What is this one?
D.
What is this one? Good. Those are the sub-energy levels of the periodic table. So if I am hydrogen and helium, I am in the 1s. What if I'm lithium and beryllium? 2s. What if I am nitrogen? 2p. 2p. Okay? Now where it gets tricky is right here. Iron. It's not 4d. Okay? Do you see what's happening? 4s, yes. This is not the 4d. So let's see why. Look at this. When I get to the 3p, so here's my electrons. They're filling 1s, 2s, 1s, 2s, 2p, 3s, 3p. That's working. Okay? 1s, 2s, 2p, 3s, 3p. But what comes after the 3p in energy? Okay? Look where 3d is versus 4s. Is 3d higher in energy or lower in energy than 4s? Higher. So the electrons will not fill in the 3d until they filled what? 4s. After they fill the 4s, then they will fill the 3d. Okay, so they're going to go here first, 1s. And do you see how I'm drawing them? I'm drawing the electrons with one going up, one going down. That's because electrons cannot fill an orbital. They cannot fill an orbital with two of them spinning in the same direction. Because if you think about electrons, they're both negatively charged, right? So if I'm going to put them in the same orbital, how are they going to do that? If they both have negative charges, they'll just repel each other, right? So I need one magnetically spinning one way and the other one magnetically spinning the other way. Let's see if you guys can do that. I can't do it. I can't do it. Okay? So one spinning this way, the other one spinning this way. Okay? Yeah, I can't do that. Okay, so that's how because magnetically, then with the opposite spins, they will be able to fill that orbital. Okay? So one has to spin forward, one has to spin reversed. So we have an up and a down spin. They'll do the same thing here, up and down. That orbital is full because it has two electrons in it. Electrons pair. That's what they do. If you have an unpaired electron, it's not happy. And then you undergo chemistry to find something to fill that void. Okay? So here, I have two paired electrons. They're happy. And then I'll continue on. Okay? Let's draw the orbital diagram for oxygen. Here's oxygen. Okay? When electrons fill into these orbitals, So in the p, there's 3 orbitals because how many electrons are there? 1, 2, 3, 4, 5, 6. So I have to have 3 orbitals. I have 3 orbitals in the p because there's 6 electrons. Now, the electrons do not fill up, down, up, down, up, down. They fill up, up, up. So there is a rule that when electrons fill, they will not leave an empty orbital. They will first put at least 1 electron into each orbital. Okay? So up, 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 and then I will come down, back down, and pair. So right now I'm right here, nitrogen. Boron, carbon, nitrogen. Up, up, up. Oxygen's electron will come and it will pair with borons. And then I will have 4 electrons in the 2p. Here's borons. Now I have 4 electrons. I just went down. Up, 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 down, down, down. That's how they're going to fill. And they will pair. How many unpaired electrons does oxygen have? This is its orbital energy diagram. How many unpaired electrons does oxygen have? 2. What does it want to do? It wants to fill those unpaired electrons. So it's going to either gain 2 electrons, or it's going to bond with something that also has an unpaired electron, or 2 unpaired electrons. What about itself? If it bonds with itself, itself has 2 unpaired electrons, right? So they will bond, form O2. That's a stable molecule. Okay, O2. What about hydrogen? Hydrogen has only 1 electron in the 1s, right? So if I put 1 hydrogen here and 1 hydrogen here, I fill those voids for both hydrogen and for oxygen. And now I form H2O. I've filled that void. I've created a stable molecule by filling those voids. Okay? So this is how the electrons are going to pair. Okay? That's how they're going to pair. So let's continue this down, down. Now I'm at neon. Okay? Sodium, magnesium. They are in the 3s. Okay? Then I go to the 3p. Up, 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 down, down, down. Now I'm at argon. And then I go to the 4s because it's the next lowest energy requirement. So I will not fill the 3d yet because the 4s is lower in energy. It requires less energy to put an electron in the 4s than it does to put an electron in the 3d. So the first D on our periodic table is scandium. It is a 3d electron. Scandium is a 3d. That's where I start filling the 3d. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. And now I have filled the 3d. And once I get past the 3d, I get here. 4p. Now I can fill the 4p. Okay? Now I'm here, krypton. Okay? So, when I look at my periodic table, and I'm asking, where does nickel reside? It resides in the 3d, not the 4d. This is a point of confusion for people because they want to read their periodic table and look at the 4th period and say, oh, this is the 4d. It's not the 4d. It's the 3d. Look at this. This is not the 6f. It is the 4f. Because I will not fill electrons into the 4f until I have first filled electrons into the 6s. It requires more energy to put electrons in the 4f than it does to put electrons in the 6s. Okay? So my periodic table is showing me, it's telling me how the electrons fill. And it has everything in order. I just have to know what that order is. How can I keep it straight? You can keep it straight by labeling the first of each group. Okay? All you have to do is be able to count to 4, which I hope you guys can do since you're in here. Okay? So, 1, 2, 3, 4. This is the 1s. This is the 2p. This is the 4f. Okay? S, P, D, F. S, P, D, F. That's all I have to be able to do. Now, I can easily identify where anything on my periodic table is. Okay? I can just label down 1s, 2s, 3s, 4s, that should be in line with that, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 4f, 5f, 3d, 4d, 5d, 6d. Okay? Now, I know this is the 3d, so this is the 4d. This is the 5d. 2p, 3p, 4p, 5p, 6p. Okay? So now I can easily identify where everything is on my periodic table. Okay? Which is going to come in very helpful here in a minute when we write electron configurations. Okay? All right. But the reason I go 4s then 3d is because of how they fill in the energy diagram. Okay? According to their energy diagram, that's how they're going to fill. Okay, so here's that how I was saying the electrons, one spins up, the other one spins down. One is south to north spin, the other one is north to south spin. Okay? And that's how they're going to go and pair in that orbital. That's how they're going to be able to do it, because otherwise they would just repel each other. They wouldn't be able to. Okay? Okay. So here's a good example of how you would generally write these orbital energy diagrams. Okay? So let's say I wanted to write the energy diagram for cobalt. Okay? So right here in the 1s, I'd put those 2 electrons, and then I go to the 2p. Next 2s. Next I go to the 2p. Up, 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 down, down, down. 3s, 3p, 4s. So I haven't got to the 3d yet. Now I get to the 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh wait, what was I going to? Cobalt. 1, 2, 3, 4, 5. Okay, so here I'm at manganese, and now iron, and then cobalt. So how many unpaired electrons do I have in the D there? 3 unpaired electrons, right? Okay, so this would be the orbital energy diagram for cobalt. Okay. And then I could always just continue onwards. Okay? And these Ds, we're going to talk about something that chromium and copper do. Okay? So let's look at the electron configuration here for chromium. 1, 2, 3, 4. Oops, 4. Okay? This is chromium. Now, when you get to chromium, so normally I would say, how many electrons are in the 1s? 2. The 2s. 2, right? The 2p. 6. The 3s. The 3p. 4s. The 3d. 4, right? Okay, well here's the crazy thing about chromium. This is not its electron configuration, just how we wrote it, okay? Because it actually steals an electron from the 4s and puts it into its empty d. So it will steal this one electron and it will put it here. So then the electron configuration of chromium becomes 4s, 1, 3d, 5. Okay? Instead of 4s2, 3d, 4. So, these all do that. These all do that. So let's look at the electron configuration of copper then. Okay? So now, when I write the electron configuration of manganese, I simply put the electron back here into the 4s. Okay? So I get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Okay? This is what stays constant. This is what's changing between those two. Okay? So this is the abnormal one. This goes back to being normal. Okay? Now, let's go to copper. So I'm at manganese. I'm going to go to iron, cobalt. So these are all following the correct pattern of electron configuration how we've discussed. Okay? Iron, cobalt, nickel, copper. When I hit copper, it steals an electron from the 4s and puts it here. Okay? So to write the electron configuration of copper, I'm going to take that electron away and put it there. So this was for chromium, manganese. Now the electron configuration of copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s1, 3d10. Okay? So it fills the D. So the electron configuration then of zinc would be what? 4s2, 3d10. It goes back to normal. Okay? So this one goes, so it's these two that are the abnormal electron configurations there. Okay? Not that electron configurations are ever normal, but they're not following the pattern. Okay? So copper, silver, gold, we have to look out for those ones. Okay? So there are questions, notorious questions about those types of electron configuration. What is the electron configuration of silver? You have to be able to recognize that that's one of the exceptions to writing it in the normal pattern. Okay? Oh, that has a full D. Silver has a full D, so it's 3D10, not 3D9. Okay? chromium and all under it. This whole column right here. Copper, silver, gold. These ones all do it. Okay? So it's that position. That's what you need to recognize. It's the position. It's the D4 position and the D9 position. Those are the ones where it does that. Okay? So you need to be aware of that. Okay. So sometimes you'll see electron. We're not going to spend a lot of time on this, but you'll see electron configurations actually written with values of N and L instead of their actual numbers, 1s, 1. This is so much nicer, but these values can also be represented. So like N, we know N equals 1, 2, 3. Those are the energy levels, right? So, and then also L would have values that would be associated with that. That we're not going to get into that. So, but that basically what those, if you ever see those, they're just telling you the electron configuration, the positions of the elements and in their orbitals. Yes?
So why is it silver always has a +1 charge if it's got a nice full? Why does it?
Well, and why doesn't copper do it, but silver does? I'm not sure. But it does probably have to do something with the fact that it only has one valence electron. Silver. How many valence electrons does it have? It's the 4s, that's the outside, right? And it only has one valence electron there. So probably loses that one and gets back to, now it has, its D is still full, but it loses that one electron.
Yeah, so the 4s is
outside of the D, yeah, it's on the outside.
Yeah.
But copper doesn't do that. I mean, so the thing about the reason, and copper can have multiple charges. It can have +1, +2, +3, plus. I don't think we get +4 very often on copper, but so it can have multiple charges, right? So, but that has to do with the fact that these electrons are kind of mobile between the S and the D. So if I lose an electron on the S, the 4s, maybe I only lost that one. Copper 1's common, but copper 2 is also common. So, well, that means that this guy went back out there and we lost him also. So now we lost both of those outside electrons, or just one of them. So the D's are weird like that. But the fact that silver is only +1, I'm not exactly sure why that is. Okay. But yeah. And cadmium is always +2, probably for the fact that it, actually these guys are often +2. And that is probably because these are full and they have 2 valence electrons and they lose those. So that makes pretty good sense right there. But you're right, this silver one, it's like, why is that? But copper's not doing that. Gold doesn't do it either. So it's a strange phenomenon. Okay, so the periodic table, as we've been looking or seeing, is designed to tell you the positions, the electron configurations, based on where they are in the periodic table. So these are all the S's. These are the P's, the D's, and the F's. Okay? So I can come in here and look at the position of an element like iodine and say, what is its position according to its electron configuration? Well, it's in the P, but which P? 2P, 3P, 4P, 5P, but it's 5P what? 1, 2, 3, 4, 5. It's the 5th element in the 5P. So it's 5P, 5. Okay? 5P, 5. 4P, 1, 2, 3, 4. Selenium is 4P, 4. Okay? Nickel is 3D, 1, 2, 3, 4, 5, 6, 7, 8. 3D, 8. Those are their positions as they're found on the periodic table. Okay? All right. So here they're going to walk us through some electron configurations. If I was writing it, here's the orbital diagram. For hydrogen, here's its electron configuration. Hydrogen has 1 electron in the 1s, so we say it's 1s1. Helium has 2 electrons. We can see here's the 2 paired electrons in the 1s. And here's the orbital diagram for helium. We have those 2 electrons in the 1s. We have 1s2. Lithium. We have a 1s and a 2s. So we have, this is full. This is only 1 electron for lithium in the 2s. So we say 1s2, 2s1. What I want you to realize is all I'm doing is I'm reading my periodic table. 1s, 2s. Lithium is 2s1. Beryllium will be what? 2s2. What's next?
2s3.
There's no 3 in the S. You can only ever have 2 in the S.
3s.
Mm-hmm. Read your periodic table like it's a book. 2p1. Sorry, I need a drink of water. 2p1. That's boron. Okay? 1s, 2s, 2p. There's only 1 electron in the 2p. Okay? What's next? 2p2. Now? Okay, good. Look at nitrogen, 2p3. Oxygen, 2p4. 2p5, 2p6, and I get to neon. Okay? So I'm just following my periodic table. Where do I go after here? 3s1. Sodium. 3s2. Magnesium. Okay? So I am simply reading my periodic table. That's all I have to do. So I don't know if some of you learned this funky thing where you had to go back and forth, back and forth, back and forth. Okay? This is 1s, this is 2s, this is 2p, 3s. Okay? I don't know if any of you did that thing. I hate it. Because it's trying to make you memorize something that you don't have to memorize. All you have to do is read your periodic table. All you have to do is follow this. This will tell me exactly where I am and what my electron configuration is. As long as I remember, this is not 4D, it's 3D. 1, 2, 3, 4. Just count to 4. 1, 2, 3, 4. And I will know where I am. Okay? All right. You can abbreviate electron configurations. And the way that I abbreviate them is simply by showing the noble gas that comes before the electron configuration. So, for example, sodium. Here's sodium, number 11. Here's the noble gas that came before it. So, to write the abbreviation, I simply put neon in brackets, meaning the electron configuration of neon. So I don't have to write 1s2, 2s2, 2p6. I don't have to write that because it's already understood that that part is this part. And then I just have to continue from that point. Okay? 3s1, that's the abbreviated form of the electron configuration for sodium. Now, for sodium, it's not a big deal to write that out. But when you're down here on iodine or something, okay, you can imagine the electron configuration is getting pretty long. But I'll still make you write some of those long ones, okay? But sometimes I might say it's okay to abbreviate it. And then for iodine, I would abbreviate it by saying the noble gas that comes before iodine is what? Krypton. Okay? So I'm going to go from 36 to 37. Where am I? 5 what? 5s2. Good. 4p10. To iodine. 5. Good. So 5s2, 4p10, 5d5. That's the electron configuration of iodine. Oh my gosh. Yeah. What am I doing? Thank you. So I'm still recovering from earlier this week, all the stuff I was doing. Okay. Okay, so 5s2, 4d10, 5p5. Okay, that's the electron configuration for iodine. All right. Okay. We're okay with that. Phosphorus here, it's another look at it. 1s2, 2s2, 2p6, 3s2, 3p3. So that would be the electron orbital diagrams there. Okay. With these things, the main thing you need to remember is you don't go up, down, up, down. Okay, because if I did, then this would be like that, and I would only have these 2 boxes filled. That can't be the case. You have to have all 3 boxes filled before you can pare down. Okay? So before you pare down, make sure all 3 of those boxes are filled. Okay. All right, now let's talk a little bit about some of the trends. Well, actually, no. Let's practice writing some electron configurations. Okay? So, silver. Write the electron configuration of silver. Fine. The abbreviated form. No. I want you to write the whole thing. You need the practice right now. So go ahead and write the entire electron configuration of silver.
Silver's doing the same. It's taking that 1 from the 5s, right?
You gave it away. Yeah. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Oh, Thank you for correcting me. 5s1, 4d10. Gosh. I'm still in intro mode. We don't learn that in intro chemistry. Okay, so 4d10. That's the electron configuration for silver. Okay, so if you had done that, then yes, you would say Kr 5s1 4d10. So depending on what I ask you to do. If it's okay to abbreviate, this is fine. If I don't tell you, I will tell you if I want you to do it this way. If I say write the whole thing, then do that. Otherwise, you can assume you can abbreviate it.
So at 06 is from the S bracket before those, not the 4S?
Not the 4s.
It's the S bracket before.
Because that's the valence shell. That's the outside shell. The 4s, they're safe. They're inside. They're okay in there. So they're okay. Okay, let's try one more really quick. You can do the abbreviated one. Let's do it for lead. What is the electron configuration of lead? Abbreviated. The abbreviated electron configuration of lead. Okay, who can tell it to me? What's next after XE? 6s2. Then? No. 4f14. And this is how you can know that. Look at this. 56. 57. 71. 72. Okay? 4f14. 5d10. 6p2. Okay? So that's how you would write that electron configuration for lead. All right, we'll see you guys next time. Yes, we will.